Hello everyone, how are you all? Well guys, welcome back to Vedantu's JEE channel. All you students who are moving from 11th to 12th standard, you know that this is an exclusive session and exclusive series that we have started for students who are moving from 11th to 12th standard. Okay, so guys, this is the very first chapter that we are studying in physics. The name of the chapter, as you all are aware, is electrostatics. And right now, in this session, we are going to talk about electric fields potential and electrostatic potential energy. That means today's discussion is going to revolve around how much amount of energy is going to be stored in the case of electric field. So guys, in 11th standard, if you all have paid good attention to the chapter of gravitation, you are going to find this very easy. If you were not one of the fortunate ones, then don't worry. Today the concept is going to get clear. Okay. So guys, before I get into the discussion of electric potential and potential energy, let me introduce myself to people who are here on the channel for the first time. Okay, so guys, if you are here on the channel for the first time, this is me, your Suri Sir, also known as Mogambo on this channel. Why? Because when my students will crack the examination of JEE, then Mogambo khush hoga. Okay, people, if you are here on the first time for the channel, then you also need to know the schedule that we are following for students who are planning for appearing for JEE on in the year of 2021, that is next year. So this is the team of the teachers, and the schedule is also there for all of you. Yep, this is Harsh sir, and he is your chemistry guru. This is Arvind sir, guys. Okay, he is teaching you all mathematics, an amazing teacher of mathematics. And this poor person is me. Yeah, and I'm going to try to teach you all physics. So all those 12th students who are moving from 11th to 12th, remember that 9 p.m. is a very important time for you every day, because 9 p.m. is the time when we meet for theory sessions every day, and 8 p.m. on selected days we do MCQ problem solving. So guys, on Mondays and Thursday at 9 p.m. you will meet Harsh sir for chemistry. On Wednesday and Saturday at 9 p.m. you'll meet me. Like today we are meeting on this Saturday, and on Tuesdays and Fridays at 9 p.m. you'll meet Arvind sir to learn mathematics. But on Monday, Wednesday, and Thursday at 8 p.m., we are going to do MCQs related to physics, chemistry, and mathematics. Okay, guys, I hope it's a very simple schedule for everybody to remember. Every day, remember 9 o'clock is definitely the time that you have to be here. And on Monday, Wednesday, and Thursday, you should be on the channel to do more of MCQs with us. Okay, so, people, if you are really serious about preparing for JEE 2021, then you should know that during this lockdown, even when we are not able to go to our classes and our school, at Vedantu, everything is free of cost available for you. For students who are going to prepare for JEE 2021, guys, all you have to do is follow this link, download the Vedantu's app, and come for Vedantu Pro classroom course, in which right now the enrollments are also free of cost. You know that right now on Vedantu's platform, all the content is available for you, most of them free of cost as well. So if you want to study beyond this YouTube session, you can come for our Vedantu platform course as well, guys. Okay, it's free of cost for all of you. So do come, enroll right now, and I'll see you in the classrooms as well. Okay, not just me, Harsh sir and Arvind sir as well. Okay, so apart from that, yes, if you are on the channel for the first time, guys, then in that case, it's recommended to subscribe to the channel as well. Why? Not just subscribe, also hit that bell icon, because anything which is happening on this channel right now is really important for you. You don't want to miss out on any of those things, so you want the notifications and you want to be updated with respect to this with respect to this channel. So subscribe right now, and stay tuned to all the awesomeness which is going to happen on this channel. So guys, let's start the session now. And as I said, today's session is about electric potential and electric potential energy. Okay, so if you will try to go back mentally and think about the chapter of gravitation. So far, the chapter has been resonating a lot with the chapter of gravitation. There we saw a formula of force of gravitation which looked like G m1 m2 by r square, and here the formula for force became K q1 q2 by r square. So a lot of resemblance, right? If I speak about there, we talked about gravitational field. It was force of gravity per unit mass, which became G capital M by R square for a point mass. And here the electric field was defined as force per unit charge, which also resembled very much because the formula looked like KQ by R square. Okay. So guys, if you remember, the idea of defining gravitational field was to be able to calculate the force if you are aware about the value of G. You can just multiply the value of small g with a mass and you'll be able to calculate the amount of force which was experienced by that mass in a given gravitational field. And similar was the logic of defining the electric field as well, which means what? If I'm interested in calculating the value of the electrostatic force, all I need is the value of electric field and the charge which is moving in this electric field, which is present in this electric field. You'll be able to calculate the electrostatic force which is experienced by that charge in that external electric field. Okay, guys. Now, why am I speaking about all this? Is because very similar are the concepts that you learned in the chapter of gravitation related to gravitational potential and gravitational potential energy. If you guys remember, the gravitational potential expression used to be Gm by R with a minus sign over there, and the potential energy for two masses used to be G m1 m2 by R. Okay, so stay tuned. I'm going to tell you that it's very easy to remember the formula in the case of electrostatics because they are going to look very much similar to these. Okay, so we'll come back to these formulas to compare our formula as well. Okay, and right now all we'll do is go back to the basics and think about how we used to define the potentials over there and the potential energy as well. Okay, so the story actually starts from work, power, and energy, as always. I always say this, and I'll repeat this one more time, that the chapters that you studied in mechanics in 11th standard, yeah, the chapters of kinematics, laws of motion, work, power, energy, center of mass, and collision. These chapters are one of the most fundamental and most important chapters of entire 11th and 12th standard physics. In fact, a lot of these concepts are going to be very useful when you will, get into your further studies after your school education. Okay, so guys, coming back, not getting carried away. In the chapter of work, energy, and power, we understood that the potential energy change is only related to the work done by conservative force. And how they were related? That potential energy change is negative of the work done by the conservative force and is equal to the work done by the external force. Means what? Say if there is a body and this body is being taken in this direction by some force. So let me just change the color to show the direction of force also. Say if this is the force which we are calling as the conservative force. So in this case, if the conservative force is taking the body in a given direction, and say when we are trying to talk about the potential energy, we say that body is experiencing no change in kinetic energy. That means the net value of kinetic energy remains constant. So I say that that is only possible when the forces which are acting on the body are zero, which means what? The value of external force in magnitude is equal to the value of the conservative force Fc. Okay, and if you speak with respect to direction, then their directions are just opposite. Okay, and that is why the equation which is written above makes sense. Means what? If you will try to calculate the work which is done by your conservative force over here, if you'll try to calculate the work which is done by your conservative force, say that work done in this diagram looks like it will come out to be positive, then certainly the work which is done by the external force will come out to be negative. That means what? The nature of external force work and the conservative work is definitely going to be just opposite. Okay, I hope you are able to remember and you are able to again look back what you studied in 11th standard. So this is very important to again understand here that what we are going to study in terms of electric potential energy and electric potential, uh, we are going to talk about a lot of things which we have studied, or rather, we are going to gain a lot of our concepts which we have studied in our 11th standard. So let's go forward. Let's first talk about the expression for work done to move a charge in an electric field. So let's try to visualize. Say we have electric field being created by a given charge, and this electric field has these electric field lines, and say these are two random points in the space, and those random points are the points in which we want a charge to be moved from point A to point B. Say that charge that we want to move from point A to point B is a charge Q, and we want this charge to take this path while passing through this electric field. Okay, if you want, you can also think in the directions of gravitational field, and the mass is being moved in that gravitational field. Okay, so what we are interested in is to find out the work which is done by the, say, the external agent, or maybe the conservative electric field force. Okay, so during this path, when the body is of the charge is being taken from point A to B, assuming that, or other, not even need to assume, you can see that the electric field is not uniform because the field lines are not looking or representing to be any uniform electric field. So definitely the force which will be applied on the charge by this external electric field is not going to be a uniform constant force. So you cannot directly just calculate the work done by writing force into displacement into cos of theta. Okay, because both the electric field is non uniform, as well as the angle between force and displacement you will see is not going to be constant. So if you will look at this point where I'm talking about dividing the entire path into small displacements dl, say at a given point in the path of the charged particle, the direction of the electric field and dl are making some angle theta, such that the electric field is creating a force on the charged particle, which we know how to find out as QE. I've spoken about this in the beginning today. Okay, so the electric force acting on the charged particle during this path is Q into E. Okay, and electric field is obviously going to be variable. That's the best case that we are considering. And as I told you people in the previous slide, when we are talking about the potential energy, we need to think with respect to external force as well. So say that when the charged particle is moving, we are not letting it gain any kinetic energy. That is only possible when the net force acting on the charged particle is zero, which simply means the external force which you can see here is exactly equal to the electric force in terms of magnitude. Okay, that means what we are trying to say here, that your F external in magnitude is equal to F electric. Okay, at least in terms of magnitude I can say this. Q into E is the magnitude. Okay guys, so now when it comes to calculating the force, we have got the value of external force. Now we want to talk about the work which is done by the external agent. Why? Because then we'll talk about the change in potential energy eventually. Okay, so guys, let's talk about the work which is done by the external agent, and that is going to be nothing but force into displacement, their dot product, F dot dl, and the body is being taken from point A to point B. What is F external, guys? It is nothing but QE, and direction wise it is opposite, so that's why minus QE dot dl. You can see that charge not changing magnitude wise while moving from A to B. I can take this charge outside, and the work done in making this charged particle move from point A to point B in this external electric field looks like the expression that you see here, which is minus Q in integration E dot dl, while the charge is being taken from point A to point B. Okay, so guys, somehow we have found the expression of work done, which actually is very much similar to what we have seen in the case of gravitation as well. There the work done by the external agent used to come out to be minus of mg dot dl, in the obviously in an integral sign. Okay, now why we have found this and how it is going to be useful is in defining the expression of electric potential, which is obviously again very similar to what we have studied in 11th standard in gravitational potential. I hope some of you remember this as well. Electric potential, let's have a look at the definition and the understanding of it. So in the electric field, if we are considering a point P, and we want a charge particle to be taken from infinity to that point. In the previous slide, we talked about charge particle Q being taken from point A to point B. We are modifying that definition, or rather, we are talking with respect to that definition, and we are defining the electric potential as the work which is done by the external force. Look at this. The electric potential at a point P in the electric field is defined as the work done by the external agent force in bringing your unit positive charge slowly from infinity to a given point. This word slowly is very important because the external agent is actually working just exactly that much as much your electrostatic force is working, so that the net force acting on the body is zero and it is not gaining any kinetic energy. Okay guys, so this is basically what is happening now. We can say that a unit positive charge, that means a charge whose magnitude is 1 coulomb, is being brought from point A to point B only, but the work which is done to bring it from infinity to point B, which is A to B. More importantly, the work is done in bringing a unit positive charge here. Okay, I hope you are getting this part. Okay, so we are specifically talking about a particular case of work being done in making a body move from point A to B, but point A is a point which is at infinite separation, and point B is right now a point which is present in the electric field of an external charge. And the charge which is also moved from, say, from point infinity to this point P is also a specific charge. Its magnitude is 1. That means what we are trying to do here, we are basically trying to define the potential as work done in bringing a unit positive charge from infinity to a given point. Okay, so guys, if we talk about the expression here, the work done, which we have already found on the previous slide, is minus q integral of E dot dl. Now this has got reduced to infinity to p, and your charge has also become a unit charge. So that's why, as I said, potential is work done per unit charge, and the expression for potential at point P in the electric field E comes out to be minus of E dot dl. Okay guys, in very simple words, if you'll have to understand, electric potential, my dear friends, is nothing but work done. Means it's a scalar quantity. It is just like work done. It is just that work done in general is defined for any object to be taken from one point to another. Whatever is the work which is done by a force in making a body move from one point to another. Potential, on the other hand, is a specific type of work done which is defined for a unit object, be it unit mass in gravitational potential and unit charge in the case of electric potential. Okay guys, so that's why what you see here, if I divide this by charge q and if I divide this by charge q, the expression will look like what you are seeing here. So it's nothing, work potential is nothing but work done per unit charge. Okay guys, I hope it's making sense. Okay guys, now let's talk about potential of a point charge. So now, assuming that you are interested in finding the potential due to a point charge, not a continuous system but a point charge. So we have a point charge whose magnitude of charge is capital Q, and at a distance r from it there exists this point P, and obviously at this point we are interested in talking about the potential due to this charge, which simply means what? There has to be a unit charge which is brought from infinity to this point P in the electric field of this charge capital Q, which is right now our point charge. Okay, so what we have defined here, guys, we have defined the potential as integral of E dot dl. Yes or no? When the charge is being brought from infinity to a given point P, and point P is at a distance r. Okay, how will I write this E, say at a given point in this path? As you know that electric field because of a charge is kq by r square. So say at a distance L from it, there comes a position where the charge is being moved by a very small amount dl. And here the electric field due to charge capital Q is E. Okay, so what is the value of E? E is kq by L square and the amount of displacement is dl. So in the dot product, let's put it as kq by L square dot dl. Okay. So assuming that when the charge was brought, it was brought along the straight line, assuming that the angle between electric field and dl vector is either 0 degree or 180 degree in this case. And by the way, there was a minus sign here as well. So considering that minus here, so overall, if I assume that theta is equal to 0 degree for this case, the charge is brought along a straight line. So in this case, kq is the constant part and integral of my L to the power minus 2 dl is what we are interested in. So when you integrate it from infinity to r, say minus kq, and integration of this will come out to be minus 1 by L. You can integrate it very easily and you put the limits from infinity to r. The final result of potential will come out to be minus kq minus of 1 by r plus 1 by infinity. So this part obviously becomes 0, the 1 upon infinity part, and final result of the potential will look like k q by r. Yes, dear friends, very similar to what you studied in gravitation. And in gravitation, the expression of potential used to be G capital M by R, but with a minus sign. You remember that? So this minus sign over there was always there. But in the case of charge, if the charge is positive, the potential will be positive. If the charge is negative, then the potential will come out to be negative. Okay. So guys, I want you people to remember the similarities and more importantly, remember the expression. The potential due to a point charge comes out to be at this point K capital Q by R. Okay. Okay, guys. Moving on. Let's speak about potential due to system of charges. Means what? Now, what if you have multiple charges Q1, Q2, and Q3 being present, and under the influence of their collective electric field at point P, we are interested in bringing a unit positive charge from infinity to this given point. So, as I said, guys, electric potential is nothing but the work done in bringing a charge from one point to another, right? It's just that charge is unity, its value is 1. So because potential is nothing but work done, the value of net potential is also going to be calculated exactly the way net work done was calculated. And that is nothing but calculate the work which is done by all three charges and simply add it because work done is a scalar quantity. Okay, so let's do that. So if I say that due to Q1, the potential at P is V1, and due to charge 2, the potential at P is V2, and due to 3, say the potential is V3, and not just that, say there are multiple charges. So you are going to simply add the potential due to all of them, and you will be able to calculate the potential at that point due to multiple charges. Okay, so let's do that. So you know that because of a point charge, potential is written as kq by r. So because of q1, the potential is going to be kq1 by r1. Because of v2, potential is kq2 by r2. Similarly, because of q3, it is kq3 by r3. So on these lines, you'll be able to find out the value of net potential, say at point P. Okay, guys. I hope that's quite easy to understand if you have understood the expression of electric potential due to a point charge. Okay. Okay, guys. Now, this was so far we are speaking about a situation when the charge was brought from infinity to a given point. Now, what if you are interested in talking about the potential difference between 2 points among which none of the point is located at infinity? So in that case, what? The potential difference is what we are going to define here, which later on in the chapter of current electricity will become the voltage difference also. Okay. So Say, going back to the definition of work done that we talked about, when the charge was taken from point A to B, whatever was the work done, now it's going to be a unit charge which will be taken from point A to point B, or you can say the total work done per unit charge is how you are going to define the potential difference. Means what, guys? To find out this value, we can also say it is nothing but the potential due to a charge, say capital Q. Say this is a capital Q charge which is creating this electric field, and say it is at a distance RA and RB respectively to these points A and B. So potential difference at B minus potential, rather potential at B minus potential at A is nothing but KQ by RB minus KQ by RA. This is how you can find the value of the net potential difference as well. All you need to do is either be able to calculate the work which is done in taking the charge from A to B and divide that by the value of the charge itself, or secondly you can talk with respect to the potential values at A and B because of this charge which is creating this potential difference. Okay, all you should think in this case right now, guys, is that unless this charge is present, this small q charge, or you can say the unit positive charge, will not experience any uh, kind of attraction or repulsion or any kind of force. For this to experience a force, there has to be another charge which is present in the vicinity. And if that charge attracts or repels, the external agent will require to work against the force which is applied by that external charge in making the small charge q to move from point A to B. If there is no charge present, you don't actually need to do any work. The work done will become zero. So no potential difference. All the points will be at same potential. Okay. I hope the situation is becoming clearer to all of you. Okay. Now, guys, time has come to talk about the potential energy. I will try to again attract your attention towards the discussion where I said that we defined the electric field as F upon Q. The logic or the reason of defining electric field was actually to be able to calculate the force as QE. Means what? Say because of a continuous charge system, if I'm able to find out the value of electric field, if I already know the value of electric field, I only need to know the charge which is brought in the electric field, in this electric field. Say if you know the value of electric field due to a rod, an infinite rod. If you guys remember in the previous session, we found out the electric field as 2k lambda by r. So if I know this electric field and say there is an external charge small q which comes in the vicinity of this charge at a distance r, then all I need to do is multiply this by q and I'm sorted. I'm getting the value of the force which will be experienced by this charge. That's basically the whole logic of defining the electric field, and this logic could be even easily understood. This logic could be even easily understood when we speak with respect to the gravitation. Why am I again and again calling back your understanding of gravitation? Because there are a lot of similarities. You should know that when you calculate your own weight, you just calculate your own weight by multiplying the mass of your body with the value of acceleration due to gravity. You say that your body's weight is mg. You never calculate your weight as g m1 m2 by r square. What we have rather done, we have found the value of g because of earth, which is say 9.8 meter per second square. So you just multiply your own mass, say that is 45 kg or maybe 50 kg, whatever is the value of mass, you multiply that with the value of g and you say that is your weight. Yes or no? Yeah, because it's practically very difficult to be able to find out the value of g m1 m2 by r square because of the involvement of r, small r. You don't know how far you are from earth's surface, especially when we are talking with respect to different altitudes. Okay, so it's, instead of that, it's easier for us to be able to calculate the value of small g. Similarly, we define the electric field so that we can calculate the value of electric force. On the same lines, we defined potential so that we can calculate the value of electric potential energy. Let's have a look at the definition first. Electric potential energy is defined as the energy that is stored in charged particle system due to the work which is done on it by external force in bringing it slowly from infinity to a given point. Let me make it very easily understandable to you. Say there is already a charge present, like Earth, and there is another charge which is being brought from infinity to a given distance from the Earth. So the amount of work which will be done by the external agent in bringing that mass, that charge from infinity to that given point, is what you define as the potential energy. Means what? Assume that a charge capital Q was already always here, and this is infinity, and you have a charge Q which you want to be brought from infinity to a given point P, which is at a distance r from this charge capital Q. So the amount of work which will be done by the external agent in bringing this charge from infinity to this point is basically what we define as the electric potential energy here. Okay, and how we are going to mathematically write it? We are going to write it mathematically in a very simple way as Q into V, exactly on the same lines as the reason of defining electric field was just multiply the charge with the value of E, you get the value of force. So here you just multiply the value of Q with V, you are sorted, you will be able to calculate the value of U. Means what? Because of this charge Q, if I know the value of electric potential at point P, if I know this value of electric potential, all I need is the value of the charge which is brought from infinity to this point at a distance r. Multiply this by this charge q. You know the value of the electric potential energy that will be stored between small q and capital Q when they are separated at a distance r. Okay, so let's speak about that in detail. Say you have a charge q1 which is already placed, and from infinity you are bringing a charge small q2, and you're placing it at a distance r over here. So if I say that this point is P, the potential of charge Q1 at this point P is, say, K Q1 by R, and we are interested in finding the value of potential energy. Okay, so the potential energy will be calculated as Q2, the charge which is being moved, multiplied by the value of the potential at that point P. That means what, guys? It is nothing but Q2 multiplied with K Q1 by R. So the value of potential is nothing but, potential energy is nothing but K Q1 Q2 by R. As simple as that. Okay. So all you did was, whichever charge is being moved from infinity to this given point P, just multiply the value of that charge with the potential due to other charge at that point. So Q1 की वजह से all I needed was the value of potential at a distance r, and then multiply it with the value of Q2. You are sorted. You are aware about the value of the potential energy between the two charges when they are separated at a distance r. K Q1 Q2 by R, not R square. Okay. Similarly, say if you have multiple charges, say if you have three charges, and you are interested in talking about the potential energy of system of three charges here. So assuming that Q1 came first, then at a distance R1 from it came charge Q2, and then finally a charge Q3, such that the separation between them is R13, R23, and R12. So when first only charge Q1 came, okay, when only charge Q1 came, there was no other charge, so there was no work which was required to be done. But when charge Q2 came, Q1 was there to create the electric field, so some work was done. So they stored some potential energy. So overall potential energy when I'm writing, that is K Q1 Q2 by say R12, which was stored when only Q2 came in the presence of Q1. And after that, when Q3 came, guys, it came in the presence of electric field of Q1 and Q2. So it's going to store potential energy with both Q1 and Q2. So that's why K Q1 Q3 by R13 and K Q2 Q3 by R23. Okay, I hope it's visible to all of you. Right now, what you see is basically the expression overall energy which is stored in the system of three charges. If you will have four charges, you will consider all such pairs. Okay, guys. So this is basically the total work which is done by the external agent in bringing all the three charges from infinity to put them in an arrangement like this. Okay, guys. So this is the potential energy due to three charges, and I'm sure you'll be able to find out the potential energy due to multiple charges. Okay, guys, awesome. So this brings us to the end of this session. If you guys are interested in getting the assignments as well as solutions of the assignment which we give in every theory session, yes, obviously the assignment will be there in the present session as well in the description of this video. So apart from the YouTube session, if you are interested in getting more assignments, study materials, and the daily updates of things which are happening on this channel, so you guys can come to our Telegram group as well. Okay, so how can I join this Telegram group, guys? You can see this, the link, it is available in the description of this video. Come to the channel, guys, and on the Telegram channel as well, we give you a lot of very to the point and important information related to your own preparation for JEE examination. Cool. So guys, I hope you enjoyed studying today with me. If you enjoyed this session, you learned the concept of potential and potential energy, hit that like button, guys. Share this with your friends, and more importantly, subscribe to the channel, especially when you're subscribing. Press that bell icon so that you are getting all the notifications. So guys, this brings us to the end of this session. Another interesting session has come to an end here. I'll see you again in the next week, and we'll be solving obviously MCQs. We'll be taking this chapter from here forward again. Make sure that you are watching all the videos which have happened before if you are watching this one for the first time. Okay, so that your continuity is maintained. And I will see you again in the next week. Till then, keep studying, keep enjoying physics. More importantly, stay safe at your home. Bye bye, guys. Take care.